Okay, so thanks, Jenny. Today I'm gonna talk about metacognition in red-green dichromacy. So let's start with some basics about color vision. As we, most of us here know, color vision is based on three types of cones, the L cones, M cones, and S cones that respond differently to different parts of the spectrum. So in the case of red-green dichromacy, we have two subtypes, and what happens is that these observers lack of one of the photopigments that are inside one of these types of cones. So in the case of protanopia, they lack of the photopigment that is inside the L cone. So in practical terms, they don't have any response in this type of cone. And in the case of deuteranopia, they lack of the photopigment that is inside the M cone. This has several consequences for their color vision. So in the case of the maximum efficiency function, the lambda, normal trichromats have the maximum on this point here, 555 nanometers. And in the case of red-green dichromats, this is displayed towards shorter wavelengths, as it is for protanopes, or towards longer wavelengths, as it is for deuteranopes. Okay, and in terms on how the world looks for them, we have here some simulations performed with this check. This is the web page of the Great Britain Color Group, and we have the original image here on the top, and we have the protanopia simulation and the deuteranopia simulation here. So as we might imagine, looking at this, red-green dichromats struggle to differentiate and to name colors, and in a similar way to normal trichromats. What we wanted to know with this research is how much they know about the things that they confuse. So we performed two experiments. Our first experiment was a pointing task to measure color discriminability, and a second experiment, a verbal task to measure the metacognition about their color discriminability. We will compare the results of these two tasks, and we will analyze the underlying dimensions that support the dichromat's performance on these two tasks today. So we have 48 red-green dichromats taking part. In the pointing task, there were 17 dichromats, 8 protanopes and 9 deuteranopes, and in the verbal task, we had 31, 15 protanopes and 16 deuteranopes. All of them were males. We tested their color vision with the Ishihara plates, the City University Color Vision test, and the Lantoni test. And finally, we confirmed their dichromacy using Rayleigh matches on an anomaloscope. All of them accepted the full range of red-green matches, and no participants produced triton responses in the City University test or in the Lantoni test. So these are the stimuli of the pointing task. We had 102 stimuli arranged in a matrix over a gray background. They were viewed from 50 centimeters, and each stimuli was 4 degrees of visual angle on the retina. And the observers were asked to indicate which stimuli could be named with a given basic color term. As most of us also know, basic color terms are the minimum name set that denotes consistently and consensually the color names within a language. The searching order of each basic color terms was varied randomly among observers, and the 102 stimuli were selected from the NCS Color Atlas from a previous research, and we had 3 intentions with this selection. First, we wanted to have the best exemplar of each basic color term. I will talk about these basic color terms from Spain in English to be more clear with all of you. So they were the best exemplar of red, green, blue, yellow, pink, orange, purple, brown, white, gray, and black. Then we selected boundary stimuli between these categories of basic color terms, and then we selected the stimuli halfway between the best exemplar and its relevant boundary in CA lab space. We measure all these colors with a PR650 spectrocolorimeter, and you have here in this chromaticity diagram plotted our stimuli that cover a nice part of the color space. In the verbal task, we presented this 11 by 11 matrix that, as you can see, included the 11 basic color terms in Spanish in the top row and in the leftist column. The matrix was presented in front of the experimenter and the observer, and the observers were asked to indicate the percentage of confusion between each pair of basic color terms. For example, they were asked, when red is the name for others, which percentage of times would you use the name green, and so on, with all the different pairs that fill out the whole table. So in total, they completed 110 cells of the matrix because we didn't ask them to complete the main diagonal. As you can see, these cells are presented in black because they were not asked to estimate that percentage. The different rows of the matrix were completed in random order. And here we have some of the results. In this case, we have the results of the pointing task. It's important to note here that this percentage are not hit or fails in a naming task. So we are not comparing the results with the results of a normal observer's sample. So what we are showing here is the amount of times that they were doing a specific pointing. So that means that when they selected a color sample as belonging to the red category, they didn't select the same sample as belonging to any other category, okay? So this is a specific pointing, only reds selected always as reds, and this would be the case of they are looking for reds and sometimes they select a stimuli that they previously selected as greens, okay? So in this matrix, we can see that apart from the main diagonal, when there is a specific pointing, we have 44 confusions that they actually performed when they were looking for the different basic color terms. So the gray cells mark which were the most common confusions. In this case, you can see here 3 asterisks for the blue-purple. Okay, so this asterisk don't indicate any statistical significance, just the higher percentage of our matrix. We have the second most confusable pair, that was the brown-green, and finally the pair pink-gray. That's for the pointing task in protonobes. Let's look at the verbal results with protonobes, how they think they would perform. So in this case, the first obvious result is that there are much fewer cells completed. So they estimated that they will make less confusions between pairs than they actually did. So only 33 here versus the 44 here. But if we compare the magnitude of the estimation of these confusions, we can see that the percentage in this table, the actual performance, was always lower than the percentage on this table here. So actually, if we compare green with brown, they thought that the confusion was 41% of the time, and it was actually 20% of the time. Let's look at the same results for deuteronobes. In this case, we have 51 confusions, and as in the previous case, we have fewer confusions when we go to the verbal task. And the percentages, again, much higher, in this case, in the verbal task, than in the pointing task. If we analyze these confusions combining the 2 triangles of the matrix, okay, so looking at the confusion when they were relating red-brown pair or brown-red pair, okay, we can build this table here to simplify a little bit things and see which were the pairs that actually were most confused in the pointing task, or they were estimated as most confusable in the verbal task. So we have, if we reduce the matrix that way, only 55 potential pairs to compare. And we mark in this table only the pairs that were above the 10% of confusion in both directions. That means over 10% in the red-brown and the brown-red direction. So the cells that are covered with gray and a black stripe mark situations in which that criterion was filled, and the ones that are white are situations in which this criterion wasn't happening for any type of dichromat or for any of the two tasks, okay? So if we follow this criterion, we have only 10 out of the 55 potential pairs to compare that happen to be over the 10% criterion in any of these situations, which is a much smaller number. Let's analyze by different dichromats what happened. Let's compare the two tasks. We have only 4 mismatches between the estimations of protonopes and the actual performance of the protonope. So this is a coincidence, for example. Red-orange, it was estimated below the 10%, or red-brown was estimated and actually performing above the 10%. But for green-yellow, they were, for example, overestimating because they were estimating over 10%, but they were actually performing below the 10%. So in the case of protonopes, there are 4 mismatches. 3 of the 4 are overestimations of confusion, and 1 of them is an infraestimation of confusion. We have gray cell here and white cell here, okay? So only 4 out of the 55 mismatches. In the case of deuteranopes, we have a similar situation. Only 6 out of the 55 were mismatches, but in this case, we have 3 overestimations of confusion for red-brown, red-orange, and yellow-orange, and we have 3 infraestimations for green-gray, pink-purple, and pink-gray. We use the data on the first matrices and put them into an MDS analysis to reveal the underlying dimensions that guide these dichromats in the performance of the pointing task and the verbal task. These are the results for the protonopes. We have here the results for the pointing task, and our MDS saw it at 2-dimensional solutions. So we had a first dimension that was chromatic. We had bluish in one extreme and oranges in the other, and black in one extreme in the two and white in the other. In the case of the verbal task, it's amazing how much this MDS mimics what happened with the actual MDS from the pointing task. We have also the 2 dimensions, blue, orange, and white, black, and the disposition of the rest of the categories is pretty similar in the case of protonopes. In the case of deuteranopes, for the pointing, we also obtain this 2D solution with white, black, and blue, orange in the 2-dimension. But in the verbal task, the estimations were not so much like the pointing task. So if we try to link the white and black and the blue, orange from before, we see that we don't get any meaningful dimensions this way. If we just try to link the streams of the 2-dimension, we don't obtain anything meaningful in terms of underlying mechanisms. We obtain black, orange, and white, purple, which doesn't mean anything in terms of chromatic mechanisms. But if we look at the disposition of the different categories, we can see that we have more or less all the cold colors in one side and the warm colors in the other, and also we have kind of the light colors in one side and the darker colors in the other. It's not so nicely shown, the solution, but they were, let's say, more variable, the deuteranopes. The next thing that we did was to correlate the 2 dimensions of each task. So in the case of protonopes, we have here the first dimension, the chromatic one with orange and blue on the extremes, This is the data for the pointing task, and this is the data from the verbal task. And the R-square values that we obtained were pretty high, 0.95. And in the case of the second dimension, we have R-square values of 0.93. Okay, so this is for protonyms, a high relation between the dimensions of both tasks. For deuteranobes, as expected, the results were not so high, but still pretty good. So we have 0.77 for the first dimension and 0.87 for the second dimension. And let's go with conclusions. We found strong coincidences between the results derived from the pointing and the verbal task, indicated that red-green dichromats have a very accurate metacognition about both their capacities. They have important difficulties to discriminate 10 of the total 55 VCT possible pairs, and also about their limitations. They rated as very difficult the brown-green and the blue-purple pair, and they were actually two pairs that were very difficult for them in the pointing task. We can compare the performance of the red-green dichromats and their metacognition, which of course is not perfect, with a caricature that we can see on a painting. Their knowledge about their confusion includes fewer confusions between VCT pairs. Just as in a caricature, we will include less feature in a face, but the magnitude of these difficulties are exaggerated by these observers in their metacognition. As in a caricature, we will see these fewer facial features very exaggerated and oversized. And finally, we can conclude that the MDS solutions give us, in both cases, two-dimensional solutions for the pointing and for the verbal task, and the dimensions of both tasks show high correlations between them. Finally, I want to thank Humberto Moreira and Julio Lillo, which also took part on this research, and I want to thank you for your attention.
Thanks, Leticia. I can see lots of virtual clapping and